So I think you are able to see the screen, right? So today let us start with the properties of Z transform. Last class I told you about the Z transform, the region of convergence, various properties of region of convergence, and given different sequences, how do you find its Z transform and how do you find its region of convergence? Okay, now today let me start with the properties of Z transform. So these properties make the computation simpler. That's why we go for properties of Z transform. So you have 10 properties. The first one is the linearity property, time shifting property, scaling in the Z domain, time reversal, time expansion, conjugation property, convolution property, differentiation in the Z domain, initial value theorem, and final value theorem. If you have an idea about the Laplace transform, I think it will become easier. Otherwise, also no problem. So these are very simple to follow. Okay, let me start with the first property, linearity property. Okay. So what does linearity property says? You all know about the linearity condition. So that linearity is something which satisfies the superposition and homogeneity. Same thing here. So if I have a sequence x of n which forms a Z transform pair with x of z. So you know this, I've already told you about the relationship between x of n and x of z. Okay, so we say x of n and x of z form a Z transform pair. So if x of n and x of z form a Z transform pair with ROC equal to R1. So let us say ROC for this sequence is R1. And you have another sequence y of n which forms a Z transform pair with y of z with ROC equal to R2. Then A into x of n plus b into y of n forms a Z transform pair with A into x of z plus b into y of z with ROC at least R1 intersection of R2. That is, R1 is ROC of first sequence, R2 is ROC of the second sequence. So you can see from this property that if you take some of the sequences in the time domain, in the Z domain also, the Z transforms are getting added. And if you scale the sequence by a constant, its corresponding Z transform is also getting scaled by the same factor. Okay, so that is about the linearity property. So let us prove this property. So let us start with the definition of the Z transform. We all know that Z transform of any sequence x of n is given by x of z. And how do you find that? Summation of n varying from minus infinity to plus infinity x of n into z power minus n. Now, this is in general for any sequence. Now, I have to prove for this sequence, that is addition of two different sequences which are scaled by the factors a and b. So now what I do, I'll take z transform of this summation. So z transform of a into x of n plus b into y of n is equal to what? I am taking z transform of this sequence, right? So now I have summation of n varying from minus infinity to plus infinity, a into x of n plus b into y of n into z power minus n. So I am taking the z transform of this sequence. So the given sequence sum into z power minus n. Now I'll open this bracket. The sum has two components. So summation of n varying from minus infinity to plus infinity, a into x of n into z power minus n plus the second quantity, summation of n varying from minus infinity to plus infinity, b into y of n into z power minus n. So a and b are the scaling factors which are constants. I'm taking it out. So what is being left out? This quantity. So what is this quantity? Summation of n varying from minus infinity to plus infinity, x of n into z power minus n. So this is the z transform of the sequence x of n. So this can be written as x of z. So that constant a into the z transform. Similarly here, the constant b into this is what the summation of n varying from minus infinity to plus infinity, y of n into z power minus n. So this is, we are taking z transform of the sequence y of n. So I take y of z. So on the left hand side, what I have? Z transform of A into X of n plus B into Y of n, which is nothing but A into X of Z plus B into Y of Z. So the linearity property is proved. So whatever is the scaling, the corresponding Z transform is also scaled by the same factor, and the addition of two signals in the time domain is also resulting in addition of the corresponding Z transforms in the Z domain. So this is about the linearity property. So the next property is time shifting property. So what do you understand from time shifting property? So you have two signals, x of n in the time domain and its corresponding z transform in the z domain. So in the time domain, if I shift the time in the time domain, if I shift this discrete time signal x of n by a factor n naught, then what will happen to its corresponding Z transform in the Z domain? That is what is about the time shifting property. So let us see its definition. So if x of n and x of z form a Z transform pair with ROC equal to R, then x of n minus n naught forms a Z transform pair with x of z into z power minus n naught with ROC equal to R. So the ROC will not change. Okay, because we are just shifting the sequence. So what did you understand from here? So if you shift the time sequence, that is, if you shift the discrete time signal in the time domain, its corresponding z transform, that is x of z, will get multiplied by this complex quantity. Because why I am saying complex quantity? Because you know that z is nothing but r into e power j omega raised to minus n naught. Okay, so let us see the proof. So as usual, we'll take the definition of the Z transform for any sequence x of n. So I have Z transform of x of n, which is equal to x of z, and the formula to find the x of z is summation of n varying from minus infinity to plus infinity x of n into z power minus n. This is in general. Now what I am doing, I am taking Z transform of this shift sequence. Okay, Z transform of x of n minus n naught. I am taking transform of this, right? So here, in place of x of n, for which signal I am taking the corresponding signal I take here. Okay, so summation of x minus n naught into z power minus n. Now, for simplification, we'll do some small changes. What I do is, I'll substitute n minus n naught is equal to L. So with this, your n becomes n naught plus L. So n becomes n naught plus L. Now let us substitute this in the above equation. So what is there? Z, I am taking Z transform of x of n minus n naught is equal to, now what was the index earlier? It was n, but what I did now, I substituted n minus n naught is equal to L. So the new index for the summation is L. Okay, so earlier n was varying from minus infinity to plus infinity. Now even L will vary from minus infinity to plus infinity. X of n minus n naught is nothing but L. So we have substituted L. And here z power minus n. N is nothing but n naught plus L. So minus L plus n naught. Okay. Now if you open this bracket, so I get z power minus L into z power minus n naught. Now in this, which is the quantity that varies as per the index of the summation? L, right? So I can retain z power minus L and z power minus n naught. I'll just take it out because for us it is not varying with respect to L. Okay, so I take z power minus n naught outside and summation of L varying from minus infinity to plus infinity x of L into z power minus L. So once again, what is this? Yes, it is same as your Z transform equation. Same as your Z transform equation. But only thing is, instead of the index n, you have index L. That's all. So I can replace this with x of Z. So on the left hand side, what I have? Z transform of x of n minus n naught is nothing but x of z multiplied by the complex quantity z power minus n naught. Okay, so when you shift the signal in the time domain,
Ma'am, for
the
sigma limits is from minus infinity to infinity, no ma'am. But the
uh,
notation is n naught plus L, no ma'am. It is n equal to minus infinity. N means n
no,
naught plus L.
I'm not getting what you are telling.
Ma'am, for sigma function, limits is from
Hmm.
n, no ma'am. N equal to
Yeah,
minus
that's what.
infinity to.
Yeah, I'll tell you just one. Now, earlier it was. Can you mute your microphone, please? Yeah. See here, n is varying from minus infinity plus infinity, right? So what I do, I have x of n minus n naught into z power minus n. Now what I'll do is, I'll substitute n minus n naught is equal to L. So n minus n naught is equal to L. Fine. Now the earlier index was n. Now the new index what I am taking is L. Okay. Now let us find out what is the limits for the new index. Earlier, now I am going to find the limits for new index. Earlier, when n naught is just a small value by which the signal is getting shifted. So whenever n was minus infinity, so I'll put minus infinity here. N is minus infinity and this is some shift value. Minus infinity minus n naught is what? I'm adding minus n naught to minus infinity. Obviously, I'll get minus infinity itself, right? So I get L is equal to minus infinity when n is minus infinity. So earlier it was n which was varied from minus infinity. Now I substituted n minus n naught is equal to L. Now if I substitute n is equal to minus infinity, I get L is also equal to minus infinity. That is this. And in the same equation, if I put n is equal to, that is the upper limit plus infinity, then I get infinity minus n naught is equal to L. That is, from infinity I am subtracting a very small value n naught. So I get L equal to infinity itself. L equal to infinity. So using this equation, what I do is, using this equation, you please substitute the lower limit. N is equal to minus n naught. Sorry, n is equal to minus infinity. I get L is also equal to minus infinity. Now, I substitute n is equal to infinity in this equation. I get L also equal to infinity. So, with this, the new index L will also vary from minus infinity to plus infinity, and this n minus n naught is L, and here in place of n I am substituting L plus n naught. So just one, is this clear?
Yes, ma'am.
Okay. So shall I continue?
Yes, ma'am. Continue.
Okay. Okay, so I think this is clear. After this, I've taken z power minus n naught into summation of L varying from minus infinity to plus infinity, x of L into z power minus L. So this is x of z. So we got transform of the shifted sequence is equal to, in the z domain, x of z multiplied by the complex quantity z power minus n naught. So this was about time shifting property. Okay. Next is scaling in the Z domain. Scaling, you all know. Scaling is either you expand or you increase the amplitude of the signal, or you, or the time sequence, time signal you expand or you compress. So scaling, either you can do it in x-axis or you can do it in y-axis. So let us see what is the effect of scaling in the Z domain. Okay, so scaling in the Z domain is we are scaling the signal in the Z domain, that is x of Z is scaled. So let us see what is the resultant of that in the time domain for its corresponding time discrete time sequence x of n. Okay, so let us see the definition of the property. So please understand, scaling in the Z domain means we are scaling the Z domain signal. What is our Z domain signal? X of Z. Okay. So if x of n and x of z form a Z transform pair with ROC equal to R, then I'll just go this way. Then, if x of z is scaled by a factor of alpha, can you see here? Z is divided by alpha. That means z is nothing but it is multiplied by z into 1 by alpha. So it is scaled by a factor of 1 by alpha. uh, I can say it is scaled by a factor of z is divided by a factor of alpha. So the z domain is scaled. So what is the corresponding response in the time domain? The signal x of n will get multiplied by alpha raised to n, where alpha is the factor by which the z was scaled in the z domain. Okay, so when z is scaled in the z domain by a factor of alpha, then its corresponding time domain signal x of n will get multiplied by alpha power n, and you can see ROC will also get multiplied by alpha. Earlier ROC was just R, so if x of z is scaled by a factor of alpha, even the ROC will get multiplied by alpha into R, where alpha is a complex number, any complex number. Okay. So let us see the proof. So what I do, as per the definition, I'll take Z transform of x of n. So what is Z transform of x of n? It is x of z. So what is the formula to find x of z? N varying from minus infinity to plus infinity, x of n into z power minus n. Now I take Z transform of this quantity. What is this quantity? Alpha power n into x of n. So I write here Z transform of alpha power n into x of n. So what I am doing here, I am taking the Z transform of this quantity. So wherever x of n is there, now I replace that with alpha power n into x of n into z power minus n. Now here you can see alpha and z, they have the common powers n, n. So I think I can combine them. So I have x of n and these two are combined, alpha and z. So because I need to combine such a way that it should have the same standard as per the definition. So as per the definition, what is the standard? The signal into z power minus n. So what I do, I take alpha and z. So if I just combine them, I get alpha into z power minus 1 whole raised to n. But as per the formula, I should have this quantity raised to minus n, right? So I should have a minus n here. So if I have to get a minus sign here, I can add minus sign. So this I can make it as minus 1 and this I'll make it as plus 1, so that I get the same quantity. You can just see here. Alpha raised to minus 1 whole raised to minus n is once again alpha, and z power 1 whole raised to minus n is z power minus n. So these small changes I'll do. Or this can be written as alpha raised to minus 1, z power 1 can also be written as z by alpha whole raised to n. So this is what is being whole raised to minus n. This is what is being written here. Now as per the definition of the Z transform, so you compare this equation with the definition of the Z transform, that is this equation. Now if x of n into z power minus n, the summation x of n into z power minus n can be written as x of z, then x of n into z by alpha raised to minus n can be written as x of, here because I had z here, it was x of z. Now in place of z, here I have z by alpha. So the left hand side can be written as x of z by alpha, because x of z is scaled. So z transform of alpha power n, x of n is nothing but x of z by alpha. Okay, so scaling in the z domain results in the multiplication of alpha raised to n into x of n in the time domain. So this is about scaling in the z domain. Next property. Next property is the time reversal property. So as the property says, time reversal, if the signal in the time domain is reversed. Reversed, you know what do you mean by reversing? So you are folding the sequence in the time domain vertically. So if you reverse the signal in the time domain, what will happen to its corresponding Z transform in the Z domain? That is what is about time reversal property. So let us consider the sequence x of n. Its Z transform is x of z. So x of n and x of z, they form a Z transform pair with ROC equal to R. Now, if I reverse this signal x of n, so see here, if I reverse this signal x of n, then in the Z domain, the z is getting inversed. Can you see here? X of z is becoming x of 1 over z. 1 over z is nothing but inverse of z. So even the ROC is getting inversed. So this is the response. If the signal in the time domain is reversed, then in the z domain, the z will get inverted. And the corresponding ROC is also getting inverted. Okay, let us see the proof for that. So by definition, we have Z transform of x of n is equal to x of z, which is equal to summation of n varying from minus infinity to plus infinity x of n into z bar minus n. Now I take the Z transform of the reversed signal. Okay, so Z transform of x of minus n is equal to summation of n varying from minus infinity to plus infinity x of minus n. Now I am taking the Z transform of the reversed signal into z power minus n. Okay. Now I'll for simplification, the one small change we'll make. So what we'll make is we'll substitute minus n is equal to L, like same as the previous problem. Even here the index will change now. Now I've taken minus n is equal to L. So minus n is equal to L. Now earlier the index was n. Now the index changes to L. So you can observe the change. Now as per this equation, what was the old lower limit? Minus infinity. So if I put n is equal to minus infinity, so minus of minus infinity. So L becomes equal to plus infinity. So you can see L becomes equal to plus infinity. Now what was the upper limit for n? As per this infinity, right? So if I substitute n is equal to infinity, minus infinity is equal to L. So whenever n is minus infinity, L becomes plus infinity. Whenever n is plus infinity, L becomes minus infinity. So we have, earlier it was n varying from minus infinity to plus infinity. Now with this change, now L becomes plus infinity to minus infinity to x of, what is minus n? X of minus n, L, z power, what is minus n? L. Okay. Now this in summation. So if you see, L is varying from plus infinity to minus infinity. Actually, what are you doing in this? You are just adding up all the terms of x of L, as L is varying from plus infinity to minus infinity. Now since this is summation, either you add up all the terms which are varying from plus infinity to which are varying from plus infinity to minus infinity, it will be same as if you add all the terms from minus infinity to plus infinity, because it's only summing up, right? So what I do is, instead of L varying from plus infinity to minus infinity, I can change it as L varying from minus infinity to plus infinity, because this is not going to change anything, because I'm just adding all the terms. Either you add from left to right or you add from right to left, the final answer is going to be the same. So I change L from minus infinity to plus infinity. Now, so I'll do a small change here. So this actually resembles, after changing L varying from minus infinity to plus infinity, I have here x of L into z power L. Now, if I want to compare this with the given definition of the Z transform, I cannot compare, because in place of x of n, I have x of L, but in place of Z power minus n, I have Z power L. So what I want to do is, I want to get a negative sign here. So for that, I'll add a minus such that the meaning will not change. So what I'll do is, I'll make Z inverse and whole power minus L, such that the basic answer remains the same. What is the basic thing? Z power L itself. So the meaning is not getting changed. So as per our definition, this should resemble our definition, but the meaning should be Z power L itself. The answer should be Z power L itself. So I'll do this small change. So I make Z power minus 1 whole raised to minus L. So I have here, I think you understood this. So this I have done to make this same as our Z transform equation. So I have here L varying from minus infinity to plus infinity, x of L into Z power minus 1 whole raised to L. Now, if you compare this equation with the basic definition of the Z transform, what can you infer? What can you infer? If x of n into z power minus n summation is can be written as x of z, then here in place of z I have z inverse. Can you see here? In place of z I have just z inverse. Then if you have z here, then I can write it as x of z. If I have z inverse here, then I can write this as x of z inverse. This is the Z transform equation, but instead of Z, I have Z inverse. So this can be written as x of Z inverse or x of 1 over Z. So on the left hand side, I have Z transform of x of minus n. So I got x of Z inverse. So this is the proof of the time reversal property. So as I said, time reversal property says that if you reverse a sequence in the time domain, that is x of minus n, its corresponding in its corresponding z domain, the z will get inverted. So you can see that x of minus n is resulting in z inverse. So this is about the time reversal property. Okay, the next very important property is the convolution property. Okay, so I told you this in case of Fourier series also. Same thing will remain good even here. Convolution property says that if you are convolving any two sequences in the time domain, their corresponding transform domain sequences. Here transform domain is what? Z transform. So corresponding Z transforms are getting multiplied. So that is the convolution property. So let us see the property. If I have taken two sequences x of n and y of n, so if x of n and x of z forms a Z transform pair with ROC equal to R1, and if y of n forms a Z transform pair with y of z with ROC equal to R2, then the convolution of this x of n and y of n form a Z transform pair with the product of these two transforms. The product is x of z into y of z with ROC at least R1 intersection. That is the common between R1 and R2. So let us prove this property. So by definition, we know that Z transform of any sequence is summation of n varying from minus infinity to plus infinity, x of n into z power minus n. So I'm not written that. So x of z by definition is summation of n varying from minus infinity to plus infinity x of n into z power minus n. Now this is the general definition of Z transform for any signal x of n. Now what I have to do? I have to take the Z transform of this convolved sequence. So here in place of x of n, I'll be writing this convolution. Now what I do? I have to take the Z transform of the convolution. So you can see in this equation, Z transform of x of n convolved with y of n is equal to summation of n varying from minus infinity to plus infinity, and for this is what we are taking convolution, Z transform, right? So x of n convolved with y of n into z power minus n. Now what is actually this convolution? What is actually this convolution? Mathematically it is this. This is the formula for convolution. So what is convolution? Summation of k varying from minus infinity to plus infinity x of k into y of n minus k. Okay. So in place of this convolution, we are going to substitute this. So this is this equation. Fine. So outside I have summation with index n, and inside in place of this convolution we have substituted this formula for convolution. So k varying from minus infinity to plus infinity x of k into y of n minus k z power minus n. So let us simplify that. Now what I do is I'll just interchange this order of summation. So now what I do, outside it was n, inside it was k, right? Now what I do, k I have taken outside, k varying from minus infinity to plus infinity x of k, and n earlier it was taken inside. So n is varying from minus infinity to plus infinity y of n minus k into z power minus n. Now small change, let us substitute n minus k is equal to L. So now uh, the index will change. Now I am putting n minus k is equal to L. So whenever n is minus infinity, you substitute here. Whenever n is minus infinity, L is also minus infinity. Whenever I have n minus k is equal to L. Okay. So whenever n is minus infinity, so it becomes minus infinity minus k, which is nothing but minus infinity, so which is L. So if n is minus infinity, L is also minus infinity. So if n is plus infinity, infinity minus k, L becomes infinity. So that's how the index in the summation changes. Then y of n minus k. What is n minus k? We have substituted it as L. So L, and here I have z power minus n. What is n? If n minus k is L, n becomes k plus L, right? So k plus L, I have here minus n is k plus L. So we have separated these two terms, z power minus k and z power minus n. So now we'll reorder the terms as per the index. So I have here x of k, then here I have z power minus k. Then I have y of L and z power minus L. We'll rearrange the terms such that the terms corresponding to the corresponding index will fit. Okay. So here I have taken this separately, k varying from minus infinity to plus infinity x of k, and this z power minus k, I'll put it here. Next, this summation. L is varying from minus infinity to plus infinity, y of L into z power minus L. So I have two different terms here, okay, with their z transform. So on the left hand side, I have z transform of the convolution of x of n and y of n, and on the right side, I have product of the z transform of two quantities. So the first one, you have summation of k varying from minus infinity to plus infinity x of k into z power minus k. So it is exactly the z transform equation, but instead of n I have k here. So I can write this as x of z. Yes, I can write. And this quantity is also the z transform equation. That is y of L into z power minus L. Instead of n, I have L. That's all. So this is also a z transform of the sequence y of L. So I can write this also as y of z. So I got z transform of the convolution of two sequences equal to the product of their transforms in the z domain. So this is about the convolution property. Okay, so convolution property says if you convolve any two sequences in the time domain, the resultant transforms will get multiplied in the z domain. Okay, yes. So the next one is the differentiation in the z domain. Okay, so differentiation in the z domain is you're differentiating the transform signal x of z in the z domain. So let us see, if you differentiate there, what will happen to its corresponding time domain sequence x of n. Okay. So let us see the definition first of this property. So I have a sequence x of n whose z transform pair is whose z transform is x of z. So I say when x of n and x of z form a z transform pair with ROC equal to R, then I'll go this way. Then if you differentiate x of z, okay, if with respect to z, and multiply it by minus z, then its corresponding time domain sequence x of n will get multiplied by n. So I can say if the z transform is differentiated in the z domain, the corresponding time sequence signal x of n is getting multiplied by n with same ROC. This is the differentiation in the Z domain. Okay, so let us see the proof. It's very simple. So I'll take the definition of the sequence. Z transform of x of n is x of z, which is summation of n varying from minus infinity to plus infinity, x of n into z power minus n. Now this is our Z transform equation. X of z is equal to this. Okay. Now what we do is we differentiate this equation on the both sides with respect to z. So I can say d by dz of x of z is equal to d by dz of this summation n varying from minus infinity to plus infinity, x of n into z power minus n. On the right hand side you can see I cannot differentiate this term, summation of n varying from minus infinity to plus infinity x of n. So I take d by z inside. Yeah, see here. So leaving this term, I take differentiation of z power minus n. So if you differentiate, you all know how to differentiate. We am differentiating this quantity with respect to z. So I get minus n into z power minus n minus 1. On the left hand side, what I have? On the left hand side, what I have? D by dz of x of z. So small change here. So we'll separate the z terms here. Z power minus n minus 1 is there, right? So I can separate these terms. So this becomes z power minus n into z power minus 1. And I have a negative sign here, right? So that negative sign and this z power minus 1 will take it out. and whichever is variable with respect to this index n, only those terms I have considered. So summation of n varying from minus infinity to plus infinity, now it becomes n. I have taken minus sign outside. So this is n into x of n into z power minus n. Fine. So I have here now minus z inverse. Now can you tell what can be substituted in place of this? Now this resembles our Z transform equation. So our Z transform equation, if you just remember, Z transform of any sequence x of n is nothing but summation of n varying from minus infinity to plus infinity x of n into z power minus n. This is n varying from minus infinity to plus infinity. So if I can write this as Z transform of x of n, now what can this be written as? Instead of x of n, I have here n into x of n. So I can write as per the definition of the Z transform, this part which I have encircled can be written as Z transform of, here I have written, can be written as per the definition. It can be written as Z transform of n into x of n. Okay. So this is Z transform of n into x of n into minus Z inverse. On the left hand side, what I have? I have d by dz of x of z. Now what I do is I take this minus z inverse to the left hand side. So it becomes what? This is minus z inverse 1 over z, right? So with that, this term becomes minus sign also I'll take it to the left hand side. So this term becomes minus d by dz of x of z to z. If I transfer this to the left hand side, so this is written here minus z into d by dz of x of z, and on the right hand side what I have, z transform of n into x of n. So z transform of n into x of n is nothing but minus z d by dz of x of z. So this is the proof. See here. As per this z trans, because these two form a z transform pair, right? So z transform of n into x of n is nothing but minus z d by dz of x of z. That is what we have got here. That means to say that if you differentiate the z domain signal x of z in the z domain, its corresponding time domain signal x of n will get multiplied by n. So this is about the differentiation in the z domain. Okay. So I think next is the initial value theorem. I think I'll complete this and then I'll stop. So what is initial value theorem? So initial value theorem is one where we find out the initial value of the signal. Okay, so I'll tell you what is this initial value. If x of n is equal to 0 for n less than 0, that is if x of n is causal, then limit of n tending to 0 x of n, which is nothing but x of 0, is equal to limit of x of z as z tending towards infinity. Now what we are trying to say here is, if the given signal x of n is causal. Causal means what? It is defined only for n greater than 0. So you say here x of n is equal to 0 for n less than 0 means what? It is not defined for the negative values of n. It is defined only for the positive values of n. So your x of n is only defined this side. It is not defined here. It is 0. then the initial value of this signal. So when x of n is defined only from 0 to infinity, think the initial value of this is x of 0, right? Yes. So the initial value of this signal can be found out by using its set transform x of z by applying the limits on x of z as z tend towards infinity. Please understand, if x of n is the causal signal, then its initial value x of 0 can be found out by using its Z transform x of z by applying the limits on x of z as z tend towards infinity. So if you do this, you will get x of 0. This is just by definition. From x of n, how do I get x of 0? By applying the limits n tending towards infinity. So let us see the proof for it. Yeah. So I have here Z transform of x of n. Now you have to keep in mind that our x of n is a causal signal. It is not defined on the left hand side. It is defined only on the right hand side. So Z transform of x of n is x of z. Now you can see here I've taken only from 0 to infinity. X of n into z power minus n. Now what I do, I'll just expand the right hand side. For few terms I'll expand, it goes till infinity. So first term is x of 0 into z power 0, x of 1 into z power minus 1, x of 2 into z power minus 2, so on. Now what I do is, I apply the limits on this equation as z tend towards infinity. So limit of, on the left hand side I have x of z, limit of z tending towards infinity x of z, and here also I'll apply the limit. So limit of this equation as z tend towards infinity. Now left hand side it remains same, limit of x of z as z tending towards infinity. On the right hand side you apply the limit as z tend towards infinity. What is happening, see here, I have x of 0, I don't have any z term, so it remains unchanged. So I get x of 0 itself. Here, x of 1 into z power minus 1 is there. That can be written as x of 1 divided by z. Apply this limit, z tending towards infinity. What will happen? X of 1 divided by infinity. This becomes 0. Similarly, all this term becomes 0 continuously if you take the limit. So finally, you are left only with x of 0. So this is our initial value. Fine. So I can say our initial value x of 0 is nothing but limit of x of z as z tend towards infinity. So from this we have understood that if x of n is a causal sequence, then its initial value x of 0 is found out by using x of z and applying the limits as z tending towards infinity. So this is the initial value theorem. So the next properties I'll be continuing in the next class.